All right, in this video, we're going to look at a couple of examples of volumes of solids of revolutions that are rotated about axes that are not the x and the y axis. So we're going to start with this first one. We're going to find the volume of the solid that's obtained by rotating the region bounded by the graphs of 2 sine of x. So that's our graph here in blue. And y equals 0, that's our graph in green. And we're going to look just on the interval 0 to pi, and we're going to rotate about the line y equals -2. So there's our line y equals -2. So I'm still going to redraw this graph reflected across that dotted line axis now instead of the x-axis. And our rotated or reflected graph will kind of look like that. And this is still going to create that sort of circular shape, and it's going to be, oops, we can actually see that, so we don't need dotted lines. It's gonna give us one of those washers, and we're slicing up the x-axis, so that's, or the x values, so we're gonna have delta x, and then our large cylinder that we have, so that outer circle, we need to figure out what its radius is. So we know that we're going to have pi, we're going to have delta x. We need to figure out what its radius is going to be. So it's going to start here from our dotted line and go until we hit our sine function. So it's going to be what we get from our sine function. So that's going to be 2 sine of theta, that amount right there. And then it's also going to have 2 units added on to all of our radii. So the radius is going to be sine of 2x plus 2 more units. So again, it's this amount, which we get from our sine function. That's the height we get from our sine function. Plus we're going to have, oops, didn't mean to erase, plus we're going to have these 2 units added on all the way across. Our smaller cylinder that we're, and I can spell the word cylinder. Can we know that Sarah cannot spell cylinder? At least I knew it looked wrong there. So again, we're going to have pi, we're going to have delta x. Our small cylinder that we've cut out is going to have the same radius all the way across. It doesn't change. It's 2 units from the x-axis to that axis that we're rotating about, so its radius is 2. So then our integral is going to be from 0 to pi. Can factor that pi out in front, and then we've got our larger radius. Make sure I get all my parentheses in there. Minus our smaller radius, and then our delta x turns into dx. So then if we go ahead and bring that pi out in front, and then we need to FOIL out our 2 sine of x plus 2. So we literally have to do 2 sine of x plus 2 times 2 sine of x plus 2. So there we are going to get 4 sine squared of x plus 8 sine of x plus 4, and then we're going to have minus 4. So things are actually not too bad. Those cancel, and we have 2 things we actually have to find the integral of. It's best to separate these out. And there are a couple of ways that you can look at doing, particularly this first integral, the 4 sine squared of x. Let me write our other one down here, 8 sine of x. Hopefully that one doesn't seem too hard for us to do. But what I did is I know that in my table of integrals, I have sine functions, singular sine functions, 2 powers in a lot of places. So I am going to use my table of integrals and get that this integral is going to be x over 2 minus sine of 2x over 4, and that's going to be from 0 to pi. And then my second one is going to give me, oh, I can bring that 8 out in front too, or maybe I'll write it like I did over here. So pi times 8, and then we're going to get negative cosine of x from 0. My Notability doesn't want to let me write my 0. There we go, 0 to pi. So plugging all of the numbers in and everything, I will let you do that part. But we're going to get 2 pi squared plus 16 pi for our volume that we created. All right, let's take a look at now one that's rotated around a vertical line. So we're going to again find the volume of the solid obtained by rotating the region bounded by the graphs of y equals the square root of x. So that's our kind of curvy line there. And then we've got x equals 0. That's this vertical line. And oh, I thought I'd updated that. It should be actually y equals 1. And say we wouldn't have much of an area if we did y equals 0 there. So we have y equals 1. So here's our region that we're going to rotate. I'm going to erase so we don't have too much stuff on here. So again, like we have been doing, I'm going to take and reflect those graphs across our axis. And then what that's going to do, again, is create this circular region here. And again, we have a hole. We're taking a big chunk out of our cylinder here. And when I first did this, I didn't totally pay attention that the cylinders that we're making, and so we'll start with the large cylinder, we're chopping up the y-axis. So we're going to have delta y here as our variable. And then we'll have pi. So then looking at this, thinking about, okay, what is the radius of that large cylinder? Well, it's going to start here at our axis, and it's going to go this way. And it's going to be the same no matter where we are, all the way across. Kind of like we had in the other problem with our small cylinder. And it's always going to be 4 units. So we're going to get 4 squared. So yeah, I did write that like sort of as big as humanly possible there. And then our small cylinder, good, I can spell cylinder, there we go. It's going to be pi. We're going to have delta y. So we're also going to need to take our y equals the square root of x. We're going to have to change that because our variable is supposed to be y. Change that into y squared is equal to x. And now if we look at what we're doing here with our radius, there's our radius. So if you look at the 4 units, we're going to have to take away this little amount right here. So from the y-axis, maybe we'll highlight that in a slightly darker color, that little amount right there. So from the y-axis to our square root / squared function. So our radius there, it's going to be 4, but minus that y squared. Because it's going to be, like I said, that whole way across, and maybe it's a little bit easier to see up here at the top. It's the whole way across, but we have to take off this bit right there that I'm making nice and dark. Okay, so our integral is going to go from 0 to 1, because again, chopping up the y-axis, and we'll put the pi out in front, and we're going to have that larger radius, which is going to be 16, minus 4 minus y squared, and then dy. So again, as always, we have to FOIL out this. This is something you're going to do a lot in volumes. And we'll write it down here, what we get. So let's bring the pi out, and 0 to 1. And so we have 16. What we do also have to be careful about is we have to subtract all of this FOILed out polynomial. So it's really something we need to be cautious about with our subtractions and making sure that we're distributing subtraction signs. That is something that can very easily get overlooked on these. So we get 16 minus 16 plus 8y squared. Oh, that's going to be a minus y to the 4th dy. And then we've got our pi, our 16s cancel, and we have 8y squared minus 4y dy. And then we can now take our integral. We're going to get 8/3 y to the 3rd minus 1/5 y to the 5th from 0 to 1. So we're going to get pi times 8/3 minus 1/5 and then minus 0. And we're going to get 37 pi 15ths.